Valdes, and today we're doing a chemical experiment. We're going to be scientists and we're going to do some experiments and test the effect of concentration of particles on reaction rates. Then we'll talk about what a reaction rate is, about the different ways we can affect that reaction rate, and after all about why water, a pharmacal Alka-Seltzer tablet, and vinegar can show us a very important chemical principle. What we'll be doing today is an experiment that will help us show how reaction rates change with concentration. And after we'll talk about reaction rates, factors affecting reaction rates, and how to calculate it in this example. But to get started, we need to know what we need. For this, we're going to need 8 cups of water, each one with 50 milliliters of water. And this will be a total of 400 milliliters. So you can do 400 milliliters and split it in 8. And then we have vinegar. We will need a total of 225 milliliters of vinegar, and you will see why we want that number very soon. From there, we also need 9 Alka-Seltzer tablets, or 7 if you only want to test the effect of vinegar. We've done a bonus experiment just to understand the effect of multiple Alka-Seltzer tablets placed in. And you will need a stopwatch. Stopwatch to measure time, and you will need to weigh an Alka-Seltzer tablet so we can use that to calculate the reaction rate based off the time. So, as any good scientist, I'm going to need a lab partner. And for that comes my sister, Jamia M Valdes.
Hi!
So she's going to take measurements all the time that we can use later after the experiment to calculate the reaction rate. So we'll start off with this cup, which has no vinegar. So we won't need to pour any vinegar in there. Now we need this one. This one has 10 milliliters of vinegar, which we can pour in. We're going to take 10 milliliters of vinegar and just pour it in to the water. And now we're going to put 20 milliliters of vinegar, which goes from 90 milliliters down to 70. And there we go, we have 70 milliliters of total in this. And then, in this one, we'll need 30 milliliters. 30 milliliters will bring us down to 40 total milliliters. So, glub, glub, glub. And we've got 30 milliliters of vinegar in here. Now,
Can I pour it?
you're going to pour the rest in this cup, which is going to be 40 milliliters of vinegar. This is going to be 40 milliliters of vinegar.
So how many will be remaining?
0. Pour everything.
Oh. Yay. Wait.
Everything.
This one?
Yes, everything.
Yay.
Now we're going to go to this 50 milliliter.
Oh god, do you pour the whole thing?
No, we're not going to pour the whole thing.
I want to do it.
So we have 100 here. So we're going to pour this until we have about 50. So that's about just over 25. That should get us to, that's 25. Now I have 50. And now we're going to pour in all the rest in here. And all of this.
Oh. Gosh.
Now we're going to close away the flasks and move them over here since we no longer need them. So now we're going to start by... Now this is the experimental part. We're going to take some Alka-Seltzer, we're going to take an Alka-Seltzer tablet and we're going to place it inside. 3, 2, 1. Now, don't lose your eye on it, Jamia.
I won't. Actually, if we lean it a bit, then it'll stay in the same spot.
Fortunately, there's enough vinegar so that we can easily see it the whole time.
There is no vinegar, actually.
Yeah. So we can easily see it the whole time.
Get your ready. I'll tell you. Keep your eye on where your finger's pointing. And it is gone.
56.40 seconds. Whoa, you can even see the newest remnants. They just get super white and then start fading away. Anyway,
So this one?
Yep.
56.4 seconds. Okay, next. Okay, this is me. 3, 2, 1, go.
Don't lose your eye on it.
Ew, there's a bug in there. It's almost done.
Where is it?
It's right there. I see it.
Oh, I see it too. I have to follow it.
It's right there. It's pretty obvious to see it now. No, it's not done.
Yeah, I know. I'm just getting ready.
It's almost done. And it's done.
55.90 seconds.
So it's this one?
Yeah.
55.9 seconds. This is this one.
Three,
2, 1, go. Don't lose your eye.
gotta track the position. When you're doing this, you want to track the position of the tablet. Don't lose your eye on it. You should probably lift up the cup and try to see where the thing went.
It's definitely not gone yet. There.
There it
See
is.
it?
Yeah, I saw it.
You have to get your hand ready. I'll tell you when it's over. And
Done. 54.48 seconds.
54.48 seconds. Three, 2, 1. Is this next one you and that one's me, right?
Don't lose your eye on it. Don't lose your eye on it. It's right there.
If you tilt it to the way you want it to face, then it'll face the right way.
And it'll be easier to spot.
Because it'll be in the same spot the whole time. I think that's pretty obvious. got it. It's almost done. And it's
Gone. 1 minute, so 60 seconds. 60.29.
0.29 seconds.
Now 40 milliliters of vinegar. 3, 2, 1,
Go!
hold it up so we don't lose track of it.
It looks really cool because it looks like it's having a snowstorm, but upwards. No, more of a tornado.
Yeah, it starts to form a tornado. Oh,
Ow.
Don't lose it, don't lose it.
Still there. It's like falling. It's moving sideways.
Oh, where is it?
It's
Phew. Uh-oh, where is it? I don't see it.
It's there.
I don't.
I think it's.
Uh-oh.
I think it's done.
Yeah?
It's done. It's done.
72 seconds.
Mhm.
0.49.
This one's my turn. Can you hold this, please? I'll just.
Three,
2,
1.
1, go! To make sure we won't lose it this time.
We've really got to lean it a bit. That's better. Now we'll always stay that.
Well, if you lean it too much, it could fall.
Now I can still see it.
So can I.
For some reason, it has small times where it's pressing on the floor. Where it's pressing on the floor.
It's moving.
Moving sideways.
Stop moving.
Stop moving.
Wait. I think it's done. It's done. It's done.
58.95. It's weird how much it fluctuates. We must have done something wrong. You were the one that did the 75 milliliter?
Yes, I did. Whoa.
3,
2,
1.
go. Doesn't it look so big?
And whoa, from there it looks so cool. Uh-oh. We're losing our sight. Losing it. Oh, there it is. Right there.
I see it.
Now it's moving that way. Moving. No, not
Got
that
it.
way.
It's almost gone. I'll just tell done when it's over. It went pretty high. Done.
54.47.
50. Whoa.
Oh!
So 54.47.
Now, we'll do a bonus with No vinegar, but 2 Alka-Seltzer tablets. Now I'll move this over here. Grab 2 Alka-Seltzer tablets at once, and then measure how long it takes. However, we'll have to double the mass, so the reaction rate still changes. 3, 2. So it should take as long as this, but you'll see. 2, 1. And now both of them are dissolving. So I'll look from this side and you look from that side.
They're right there. Can you see it?
Yeah, I can still see it.
Can you see it? I can, kind of.
Yeah, I can still see it.
Right here, right?
Still there? Yeah, I can oh yeah, the shadows show they're still there.
You have to be ready if that thing goes, Jose. Jose, you have to go over there to make sure that it's ready. And it's almost done. Done.
Oh wow! 1 minute. Put it in seconds. 62 seconds. No, 62 seconds. 62 seconds. 0.92. 62.92. Thanks, Jamia, for your assistance. And I guess we shall get to the reaction kinetics. So here's the reaction we just did. Each one of these molecules is sodium bicarbonate. This is pretty much what baking soda is. Baking soda is just sodium bicarbonate. It's a sodium ion attached to some carbonate. Or at least to some sort of CO3H. So the chemical formula for it is NaCHO3. Now, sodium bicarbonate isn't the only thing in the Alka-Seltzer tablet. So this, you can think of this as the tablet of Alka-Seltzer. This is the Alka-Seltzer tablet. This is the composition. So this here is citric acid, which is H3CHC. So this is H3C6H5O7. This is what we've got. So H3C6H5O7. Technically, Wikipedia would list this as C6H8O7. Look it up, I'm not kidding. But seriously, this is an incorrect way of writing citric acid. Sure, it might conserve the structure, but it's incorrect because it's defined as being a hydrogen ion bonded ionically to something. In fact, an acid is basically an ionic compound between hydrogen and some molecule, while a base is some ion bonded to hydroxide. So sodium hydroxide, ammonium hydroxide, all of those. One thing you might notice, you might think, wait, sodium bicarbonate is a base. This has got to mean something. And I'm going to tell you that this indeed is an acid-base neutralization. Now, yes, this is an acid-base neutralization. It's what gives baking soda and vinegar the ability to help heal bee and wasp stings respectively. Bee's venom is acidic, so putting baking soda on it helps neutralize it and give relief. On the contrary, the opposite is true with wasps. Wasps' venom is basic, so pouring vinegar, which is a strong acid, helps neutralize, and you don't feel any pain anymore. So, additionally, this means if citric acid is a strong acid and sodium bicarbonate or baking soda is a strong base, then this means that these two are going to neutralize in some way, and this is exactly what happens when we create sodium citrate. And we'll talk about how these rearrange. But now, the last component, water. This is what we did. We placed the Alka-Seltzer tablet, which was this, in a water cup. So you can imagine this as being the cup. And before I move on to this side, we've got to consider these as the reactants in our reaction. Reactants can differ from reaction to reaction, and sometimes reactants can turn into products and products into reactants. In this case, we can't undissolve the Alka-Seltzer tablet because it can't form spontaneously. So this is a one-way reaction. It's a one-way lane. Some reactions, though, are reversible. So now we're going to put the arrow. Now we're looking at the products. The final. This is like manufacturing a cake. The reactants are the ingredients, the egg, the flour, all that stuff, the butter. They get mixed up in this reaction, and the product is the finished delicious cake. It's a very good analogy. So the tablet and the cup react to make some water. There's still water in the cup. It's just this time this whole thing is the cup. All of this is inside of the cup. Because remember, we placed the tablet in water and it vanished. There's no tablet anymore. But what happened is these two reacted and formed sodium citrate. Sodium citrate is sodium citrate is Na3C6H5O7. So that is sodium citrate. It's just 3 sodium plus ions bind to a citrate ion. A citrate ion that has a charge of -3, supposedly, considering that we have 3 sodiums. So now we still have water, but we also made carbon dioxide, which is the thing we breathe out. How do these atoms rearrange and get you to here? What makes the reaction? How does a reaction work? So let's start by looking at how the sodium citrate forms. So the bond between the sodium and the bicarbonate breaks off. So the carbonate and the sodium, bicarbonate is broken away from the sodium. And the hydrogen ion in here, this hydrogen plus ion, is knocked out from this acid. And therefore, this technically makes this also a double reaction. So again, this is an acid-base neutralization. However, this is technically a form of double replacement because it's the ions are switching places. It's just the hydrogen and the sodium are switching bases. In fact, the result is always some compound plus water. And that's where the extra water comes from. It comes from the acid-base neutralization. Hydroxide groups break out and 3 of the hydrogens, the 3 hydrogen ions, get booted out of there. They get booted out of the citric acid and join with the hydroxide group. And that's where we get the extra 3 waters. This water remains untouched. But the question is, where does the CO2 come from? The CO2 comes from the carbonate, but the hydroxide group got chipped off, which left you with carbon dioxide. And since we had 3 molecules of sodium bicarbonate in the beginning, we got 3 carbon dioxide molecules in the end. And that's the reaction explained in mildly more depth. Now, how do we balance this equation? Because we don't have the same amount of atoms on each side. That's the definition of a balanced equation. In fact, we have 1 sodium here, 3 sodiums here, and then we don't have the same number of atoms on each side. We're going to balance that. I have 1, 2, 3. This becomes 3 sodium bicarbonate. We have 1, so we don't put anything here. 1, again, nothing. 1, again, nothing. Then we have 4 waters. Again, three more were formed from the breaking of the hydroxide groups and the sodium and the hydrogen ions from the citric acid and the sodium bicarbonate, and they came together and formed 3 waters. And then there were 3 carbon dioxides formed from the breaking of the bond between the sodium and the bicarbonate, and the bicarbonate and its hydroxyl group, which left us with CO2. Now, the question is, cool, we got this. Now the real question is, how do we find the reaction rate given the time taken? Well, here's the first thing we take. The weight of the Alka-Seltzer, one Alka-Seltzer, is 113.3981 grams. And although, of course, if any Americans are watching this video, they might want to know it in pounds, so I'm going to give it in pounds. It's 0.25 pounds. So now, let's try calculating the rate of reaction for the no vinegar 1 Alka-Seltzer tablet. So we're going to do this very quickly. I'm going to do it on over here. So we've got the reaction rate is equal to the amount of mass used up divided by the change in time. So this is something to keep in mind. We know that we have 113.3981 grams, remember grams, divided by the time, which we measured in seconds since typically we want something per second. It could be moles per minute or liters per hour, but we're doing grams per second. And it took 56.4 seconds, thanks to my excellent data collector, Jamia. We were able to get that it's 56.4 seconds. And now we calculate the rate, and we get a value of approximately 2 grams per second. That's not approximate. This is the actual value, which is a lot of decimal places. And again, typically you should want significant figures. So again, we got 1, 2, 3, 4, 5, 6. We got 7 significant figures here and 3 here. So we chop this to 2 decimal places, which leaves us to 3 significant figures, which is exactly what we need. So we figure out how to do the rates of reaction. Now, this is the time it took for the 30 milliliter solution of vinegar to dissolve when the Alka-Seltzer tablet was placed in. This is how long it took to dissolve. Combine this with the mass of the vinegar, pause the video, and try to calculate the reaction rates to 4 significant figures. Remember. Okay, so you're back. And you should combine them together and get this value. But again, slice that down to 3 significant figures and move that. That's going to be your final answer. Now here's a trickier one. You have to think this one. What is the rate of the no vinegar 2 Alka-Seltzer tablets? This is the mass of a single Alka-Seltzer tablet, and this is the time it took for them to dissolve. Think, it's a little bit larger than all the other ones, but can you see why? Okay, and when you combine these, you should have gotten a value of 3 points. Wait, that's weird. And I know you might be thinking it's weird to combine these two numbers. If that clearly does not make 3.6, that makes something more like 1.8. But bear with me, the reason why this is true is specified in the example. 2 Alka-Seltzer tablets. So we have to actually add a second one of these and smash those together into a single number. And then slam that number over and combine it with this and get your final answer, which you can chop over to 4 significant figures and get this. That's how we calculate the reaction rates. Now before you leave, we're going to look at the different factors that can affect the reaction rates. Number 1 is the concentration. Concentration, as it increases, the particles are more squeezed together. So they're more likely to collide, or in a way, colliding is the collision theory of gases. The collision theory says that if a reaction happens, then the particles will collide into each other and switch parts and done the reaction that way. Keep in mind that we are slamming things in. Of course, we are going to slam the particles as the main focus for making the reaction happen. So in this case, increasing concentration is the particles are more tightly packed together. It's like putting my hands closer together. They're more likely to touch when I fluctuate them slightly, right? It's like when they touch, a reaction happens. If they're far away, a reaction isn't going to happen. But if they're closer in, they're more tightly packed. The tiny fluctuations might cause small touches. So increasing the concentration means the particles are more tightly packed, and therefore the probability of a collision happening will increase, so they might collide with enough energy and the right orientation to make a reaction happen. Number 2, increase the number of particles to react. So in form of increasing or decreasing the concentration, that's what we did with the vinegar. So this second method of adding more particles is the same as pouring more water in. The reaction will happen faster because there are more available particles to smash into each other and cause the reaction to happen. Number 3, make sure that particles stay in their elements. If they're in a huge clump, the inside element is stuck away from doing some sort of collision with the outside world. However, when each of these are isolated, you can actually make a collision happen. And this is actually what happened when we broke the bonds. We stopped making them travel in packs and split them apart. But we decomposed them so they could smash in. For example, we need to deconnect the sodiums and deconnect the hydrogen, and then deconnect the hydroxide groups in each of them to form the carbon dioxide by the spares, smashing the hydrogen and the hydroxide together to make water, and smashing the sodiums and the citrites together to make sodium citrite. And then there's number 4, increasing the size of the particles. Increasing the size of the particles can cause a lot of smashing to happen because they're very big, so they take up a lot of space. So that particle size, though, is kind of analogous to increasing the concentration. So I won't budge on that one since that was already the first thing I talked about. Number 5, temperature. This is a popular one. Now, the thing is that increasing temperature means the particles have more thermal energy, which can be converted into kinetic energy, which ensures that they will get the right energy to slam into each other enough and hard enough to make a reaction happen. It's not like the sodium and citrate go boom, oh, sorry, I just slammed into you. It's like boom, ow, well, I guess we're stuck. That's the purpose of energy. You need enough energy for the reaction to get going. And of course, it would be useless if they slammed each other like this, because that would be the wrong orientation. Finally, number 6, the presence of a catalyst. The catalyst is something that lowers the activation energy. Activation energy can be shown by the following diagram. This is a chemical reaction. Now, this energy needed to form an activation complex, which is the middle of the reaction. This energy is the activation energy. The activation energy is the energy needed for an activated complex to form. But a catalyst decreases that activation energy, therefore increasing the rate of the reaction because the probability of the particles colliding with enough energy are higher. Additionally, thinking that C is the catalyst, in the steps of the reaction, called the reaction mechanism, C actually gets used up, but then produced and spit out later on. So overall, it doesn't do anything in the reaction. Overall, it just stays there. It just decreases the activation energy, which means that it decreases that energy needed for the reaction to happen, instead of increasing the energy that the particles have, which is the job of a temperature. And that is pretty much how reaction rates can work. And that, my friends, is reaction kinetics. So let's recap what we learned today. The first thing we learned about is that acid-base neutralizations were what's going on in the tablet and the cup. And we also learned about reaction rates. And by calculating the reaction rates, we also learned about the factors affecting reaction rates. We also learned about how elements can get rearranged, and the fact that collision theory says that particles need to collide with enough energy and the right orientation, like the clap that makes a reaction. And we also learned that the activation energy is the energy needed for the reaction to go by creating an activation complex, which is a short-lived time where the reaction is underway. And that means it's the energy needed, for example, for the sodium to slam into the citrate and form the sodium citrate inside the cup later on. And with that, good luck conducting your experiment. Thanks for watching. If you like this video, please consider liking. And if you want to get notified every time I make a new video, subscribe and ding that bell. I'll be back with another video, hopefully very soon.